In this video lecture, we're going to cover data types and type checking. And the chapter 7.1 through 7.2 of the book covers the material in this video lecture, as does my notes that you can find on the course website. So there's three ways that we can think about data types. There is the denotational view, which is as a collection of values from a domain. And if you have worked with enumerated types before, where, for example, you might say enum weekday, and then you give a collection such as, say, Monday, Tuesday, etc., then that's a denotational way of thinking of a type. It's essentially an enumeration of the values of that type. Now, it doesn't always have to be a complete enumeration. I can say integer, and we're assuming the set of whole numbers. And this denotational approach is often associated with functional programming, which is a concept we'll be getting to a little later in the course. The second way to think about types is kind of an object-oriented programming way, which is to think of abstract types. And if you'll recall, an abstract type is a set of well-defined operations that's defined on a set of objects. It's an API. And it may either be defined generically, such as a list, or it may be defined concretely, such as over numbers specifically. So when I say concretely, I mean the values may or may not have a defined type. So that's the second way of thinking about a type, as essentially an API or a well-defined set of operations. The third way is the constructive way, which is the way you're probably most comfortable thinking about types, and it's associated with the imperative programming paradigm. So constructive says we start with a set of primitive types like int, bools, chars, and then we have type constructors for creating more complicated types. And you've seen some such type constructors in the past. We have records and also unions, which allow you to overlay several different records on the same piece of memory. We have arrays, which allow you to represent a homogeneous set of values, and strings, typically a special case of arrays. They're often represented internally as arrays. You have sets, which are a mutually exclusive set of items. You have pointers to items, lists, and files. So these are all composite types that you can build up from or apply to build up more complex types from primitive types. So types have a couple of advantages in the context of languages. First, they give you some convenience in that you don't have to specify the type of operation if the compiler can infer the type of the operation from the context, and that's what we mean by implicit context. So for example, if I have int a, b, and I have the expression a plus b, then the compiler can infer from the types of the operands that it needs an integer addition, and therefore it can emit an integer addition instruction. So the implicit context saves the programmer from having to explicitly specify an operation such as an integer operation here. A second important advantage of types is that they prevent us from performing meaningless operations. So for example, we would probably think of trying to add a string to an integer as a meaningless operation. We'd hope that the compiler would catch this mistake and give us an error message. Now, type checking can't prevent all meaningless operations, but it typically can catch enough of them to be useful. And then we have a concept that we talked about earlier in the course, polymorphism. You may remember there's two types, parametric and subtype. Parametric is the type that applies to generics, where you have a piece of code and then you instantiate the generic with a parameterized type, like you say list of int, and then all the methods for that list get filled in with the int type. The second type was subtype polymorphism, where you could have an inheritance hierarchy and each subtype could provide its own implementation for a method, such as a draw method. A rectangle and a circle would have different implementations of the draw method, but they would achieve the same function, which is to draw the object on the screen. So we are talking here about parametric polymorphism and the fact that if we know that a type supports a certain set of operations, that is, it's an abstract type, then we can write a polymorphic piece of code that's going to work with all objects that support that API. So that's another advantage of having types, is that it allows us to create these polymorphic pieces of code, but also to check to make sure that the type we're using supports the right API. So you'll hear a number of terms associated with type checking. One of them is strong typing, and what that informally means is that the language prevents you from applying an operation to data on which it's not appropriate. So you saw that before where I tried to add the integer 5 to the string Brad, and that was a meaningless operation. Now, orthogonal to that is the notion of static typing. And what static typing means is that the compiler does its type checking at compile time. It checks for this meaningless operations, as opposed to something called dynamic typing, which is where you defer until runtime your type check. So you still do your type checking, but you don't check to see whether the operation makes sense until you're actually running the program. You'll notice I said that the notion of strong typing is orthogonal to static typing, because we can have strongly typed dynamic languages. In fact, Python is an example of a strongly typed but not statically typed language. In fact, most of the scripting languages are strongly typed but not statically typed. Ada, which was designed by the Defense Department in the 1980s for defense applications, is statically typed and is also pretty strongly typed. Pascal, which was developed as an instructional language in the 80s, is almost statically typed. The only exception is for unions, because if you remember, a union overlays the same piece of memory with multiple record types, and therefore when you in a piece of code see an operation on a union, well, you don't know until runtime what type of data is actually stored in that union, so it's impossible at compile time to type check a union. So that's the one place where Pascal has to do dynamic type checking, and Pascal is also pretty strongly typed. Then finally, Java is a strongly typed language, has a lot of static type checking, but it can't statically type check everything. For example, it does bounds checking on arrays, and it doesn't know until runtime whether you've tried to use an out-of-bounds index. So now that we've talked about types, we're going to move on to type systems, which is something that the compiler writer needs and also the language designer needs. So we have two different definitions for a type system. The first is going to be most useful for a language designer, and it is a mechanism to define types and to associate them with language constructs. So for example, you might define the language construct int, and then you associate that with the values 2 to the minus 2 to the 32nd up to 2 to the 32nd minus 1. And you say those are the values associated with int. So in this case, I'm actually using a denotational approach for defining the int type. The second way we define a type system is of interest to the compiler writer, because it provides a set of rules for type checking the expressions in a program. So there's three terms that are important for the compiler writer. First, there's the term type equivalence, which says when are the two types of two values the same? And this is a pretty strict definition. For example, int and int are equivalent types, but int and float aren't because they represent two different types of values. And we'll talk a little bit more about type equivalence in a moment because some questions arise. Let's say I have a type int and then I have a subrange where perhaps the subrange is limited to the integers 1 to 31. Are those types equivalent or not? Okay, typically we'd consider them not to be equivalent because they cover different domains of values. So typically type equivalence says that you have exactly the same set of values in order to be equivalent. The term that's actually more useful typically for the compiler writer is type compatibility. And it says when can a value of type A be used in a context that expects type B? And so if we have an int plus a float, well, this is going to perform floating point arithmetic. So it expects, the compiler expects to have a floating point number here, but what it has is an int. However, this is considered, or the int's considered a compatible type because it can be converted easily to a floating point number. Finally, type inference is what a compiler does in order to infer the types of expressions so that you don't have to explicitly declare the type of an expression. So when you work in a compiled language, you declare the types of variables, the types of functions, but you don't declare the types of expressions. If you say C equals A plus B, you don't have to declare the type of the expression A plus B. Instead, the compiler infers the type of this expression from the types of the operands. So it would start by saying, okay, they're both perhaps int, so this is an int, and then it's therefore going to expect on the left-hand side that C is an int. Of course, it could be the case that C is a float, in which case we have type compatibility because we know how to convert an int to a float. So for our purposes, we actually think that type compatibility is the more useful concept because it tells us what we can do. We can add a float and an int. When some of the early languages like Pascal were defined, it was thought that type equivalence was better, and so there was much more stringent restrictions on what you could do with a program, even sometimes not being able to add an int and a float unless you cast the int to a float. And that quickly became viewed as too much of a rigid straitjacket, and so type checking was relaxed so that what we really care about are two types compatible. So then, moving on from a type system, we've now defined, let's say, what's type equivalent and what's type compatible, but we still have to be able to do type checking. And to do that is actually helpful to think about it mathematically. So we often will resort to discrete math from CS311, for example, to represent type expressions. So we start with the primitive types, int, bool, char, and they're just represented as primitive types. And by the way, you can see we're using the constructive approach right now for types because we're building them up. So then you can see a record is represented actually as a Cartesian product of its fields. Hopefully you're also familiar with this kind of notation from discrete math. So the left side here denotes the parameters to the function. It takes a bool and a char, and again we're representing it as a Cartesian product, and it's being mapped to an int. Okay, here we have an array, and it's a type constructor that when applied to something of type T and an index value of type integer is going to yield a value of type T. And then a pointer is another type of expression, and we represent it as you see there as pointer T. So what type checking does in an abstract sense is it reduces each expression to some kind of mathematical expression like you see here, and then it makes sure that the type expressions are compatible. So for example, there's a simple thing. If I say A equals B plus C, what this starts with is that maybe this is an int and this is an int, so it infers that the whole expression is an int. And then maybe on the left-hand side, this might be a float, so they're not strictly speaking type equivalent, but it would accept it because they are type compatible. So then there's two major approaches to type checking. There's structural equivalence and name equivalence. And structural equivalence simply says that two expressions are considered equivalent if their type expressions are identical once we've fully elaborated them, meaning any names are replaced with their type expressions. So for example, let's say that we have struct student, and we'll give the student a name, and let's also give them age. And let's define a second struct, and let's call it address. I'll abbreviate it as adder. Let's also give it a string, and we'll say road. And let's give it an int for the street address. So I'll call it the, street number. Okay. So under structural equivalence, these two structs are considered the same because if we reduce them to a type expression, each of them has the form, not name, but string Cartesian product with int. And since both of them reduce to this expression, then they'd be considered equivalent. And you probably would not actually want something of type student to be assigned to something of type address, which is why structural equivalence has fallen out of favor. It really doesn't often lead to sensical operations. Remember, we're trying to eliminate meaningless operations. Okay, you remember we said that with structs you have to, or structural equivalence, you have to fully elaborate a expression. So for example, if we had written struct student, and then inside of it, let's actually say that we had a struct adder. Okay, and we'll just call it A. And we'll also have a string name and an int age. Okay, if we were going to compare it with some other type, we would have to replace this definition of struct A with its actual type expression. So what we would end up with is that we would have student is really something that consists of a string crossed with an int. That is the replacement of the struct adder, and then it also has a string which represents name and an int for age, and that would be its fully elaborated type expression. Okay, but as I said, structural equivalence has gone out of favor, and instead we now use name equivalence. And that means that two expressions are equivalent if and only if they are structurally equivalent without name substitution. If we have struct student S and struct adder A, then under name equivalence, these two variables S and A are not equivalent because we're not allowed to replace the structs with their full type expressions. And since struct student is not the name struct student is not the same as struct adder, the two are not equivalent. So C, C++, and Java, they all use name equivalence. Now there's also two variants on name equivalence. So we have something called strict name equivalence, where so-called alias types are considered distinct, and loose name equivalence, where the alias types are considered equivalent. So what is an alias type? Well, in C, it's the type def. So let's say that we say type def Celsius is an int. And let's say we also say type def Fahrenheit is an int. And then we declare two variables. We declare one to be Celsius, and we declare one to be Fahrenheit. And the question is, if we try to assign F to C, is that a legitimate operation? I think you'd probably agree, no, that's not what the programmer intended, because Celsius and Fahrenheit, even though they're both ints, they're different measures of temperature. Therefore, this operation should not be allowed. So under strict name equivalence, they would not be allowed, because C is of type Celsius and F is of type Fahrenheit. Whereas under loose name equivalent, they would be allowed, because we would be allowed to replace the alias type with its representation, which is int, and that would make the two equivalent. Now, before you go thinking that strict name equivalence is the way to go, let's take another example. Let's instead say that we had a type def for something called stack element. We'll just abbreviate that as stack elm, also an int. And then we have that a pop operation returns a stack element. Okay, and now we say int a equals pop my stack. And the question is, should this be considered a legitimate assignment? And I think most of you would say yes, that in fact we know that stack element is an integer, and so we expect that this pop should succeed. Well, this is an example where loose name equivalence is what we want, because we do want to replace the alias type, which is pop returns a stack elem. We want to replace it with its actual type, which is int, to say that they're type compatible. So it turns out that C and C++ use loose name equivalence, because it's considered more likely that this case comes up. In fact, if you've looked at a lot of C system functions, you'll see that they use these types of type defs, but they're really returning ints, and you are declaring your variables as ints and assigning the return values from those system provided functions to your int variables. And even though those system provided functions return type defs, everything works properly. Now, Java does not permit alias types, so it is not an issue in Java. So let's just do one more quick example here, in case you're still a little bit unsure about how types work. So let's do type def, say link, and let's say it's of type pointer to cell. Okay, and now let's say we have link, next, and last. Let's say we also have struct pointer to cell P and a struct pointer to cell Q and R, actually. So under structural equivalence, so let's start with structural equivalence, then we have that all the variables are type equivalent, because if we were to replace each of the type defs with their fully written out thing for link, you'd find that next and last are all struct cell. So under structural equivalence, next, last, P, Q, and R are all equivalent. Now under name equivalence, we're going to have that next and last, under strict name equivalence, it would be only that next and last are equivalent, and P, Q, and R would be equivalent. So under strict name equivalence, these are two separate classes, name and last, and P, Q, and R. But under loose name equivalence, then we go back to they're all the same. So under loose name equivalence, they're all the same. So it would be next, last, P, Q, and R would all be equivalent. Okay. Now, there is a nice compromise in a language called Ada, which allows us to actually specify both ways of doing things. So in Ada, I would actually be able to write subtype stack element is integer. And this would say that stack element, being a subtype of integer, means it can be used anywhere where an integer is expected. Whereas we could say type Celsius is new integer, and this is saying we're defining a completely new type called Celsius, and it should not be considered an integer. And similarly, we could say Fahrenheit type, or type Fahrenheit is new integer, and this also says Fahrenheit is a new type. It's not an integer, and therefore when we go and try to assign Fahrenheit to Celsius, it doesn't work. Okay, so moving on, the last big topic we have to talk about is in type checking. You'll remember we said that we often want to say that two compatible types can be used in the same context. And we want to be able to either let the programmer explicitly tell the compiler to convert one type to a different one, or allow the compiler to do it. So when the programmer explicitly tells the compiler to convert one type to a different compatible type, we call it type conversion. When the compiler does it, we call it coercion. So subtle distinction, but if the compiler's doing the conversion, it's called coercion. If the programmer does it, it's called type conversion. And in C, the term casting is often used for that type conversion. So at the bottom here we have a simple example where we are type converting the float y to be x, and that's going to cause the value to be truncated to 6 and the value assigned to x. And some languages actually would complain if you would simply say x equals y, because they might not consider the types compatible in this situation, because there's going to be a loss of precision if I assign y to x. Therefore, the cast in many languages is going to be necessary. Okay, but sometimes the situation is reversed. Here we have something that's considered quite acceptable, which is we're assigning y, which is a short, to x, which is an integer. And since an integer has more space allocated to it, there is no loss of precision when the short is assigned to x. And therefore, a compiler would be happy to go ahead and do a type coercion in order to make this work. So C has some fairly simple rules for type coercion. So floats in expressions become doubles if they're mixed. If short or char is used in an integer expression, then both of them become ints. And if necessary, precision gets removed when assigning into the left-hand side variable. So in fact, if we were to reverse this assignment and assign x to y, even though it's a loss of precision, C and C++ are happy to perform the coercion. What they do is they drop the high order 16 bits and assign the low order 16 bits to y. So for example, if I had written x equals 2 to the 24th, which is a left shift, plus 1 to the, or 2 to the third, and then I assigned this value to x and printed out y, y is equal to 8 because the top 16 bits are thrown out and all we're left with is the low order 16 bits. So in effect, coercion rules are a relaxation of type checking because they go from strict type equivalence to just allowing type compatibility. And there's some recent thought that perhaps things have gone too far in the direction of language compatibility, and Ada does not actually permit coercions, but it's an older language and actually was one of those rigid languages that people did not like because you had to do a lot of explicit casting. Modula 2 is a more modern language and it doesn't permit coercions. I haven't heard people say one way or the other what they think about it. Do know that C++ goes to great lengths to get type compatibility, which can be a real pain in the neck sometimes. So for example, you might have that a definition like a constructor string takes a char star, and that will produce a string. So this would be a constructor for a string. So you might have something like string A equals Brad, say, plus Vander. And in fact, a C++ compiler will treat this as an OK operation because even though it looks like a char star plus a char star, what C++ will do is realize that it can stuff a char star into a string constructor and produce a string, and therefore it really can convert both Brad and Vander to strings and do it. Now this is kind of convenient in this setting, but oftentimes these conversions can occur in settings that you don't expect, and you might want that to be an error, and in fact it turns out not to be an error because C++ goes to great contortions in order to find ways to make a type compatible. Okay, so our last topic is the different types of type conversions in C++. You have seen this form, which is actually considered somewhat outmoded at this point. And instead, when you do a cast, it's really preferred that you use one of the three types of casts shown here. So the first type of cast would be the type that you often think about. So if I want to cast, say, a float to an int, then let's say I have int a, and I could say static cast int, and then the value. So it looks like a function call, and the return type you get to specify as a type parameter. So that's what it's being converted to, and then as the actual argument you give the value to be converted. So that's what we usually think of when we're just doing a cast, like saying int 6.3. But there's also something called a dynamic cast, which is putting off the checking until runtime, and it's because we can't perform the type check at compile time. A good example is when we need to be able to downcast in certain situations. So let's say that we had something like superclass star p equals new some subclass. Okay, so we've assigned a subclass to P. And now, if we try to assign to star S, we might want to do a dynamic cast to do a check at runtime to make sure that this downcast is acceptable. And in this case, we get success. But let's say instead, now let's say later we say P equals new superclass. Okay, and now we try to say S equals dynamic cast P. And now we'd get a failure because you can't downcast the superclass to the subclass. That doesn't work. So that would get us a runtime error. And then the final type of cast is called a reinterpret cast or a non-converting cast. And it's often done when you are trying to do something tricky. So let's say that you had some high performance numerical software and you had a float A. Well, if you know something about your IEEE standards, you know that A is going to be part the significant digits, and it's going to be part exponent. So if you're trying to do really fast arithmetic, what you might want to be able to do is go in and interpret these bits right here, the significant bits, as integer, so you can do integer addition on them, and maybe then do something clever with the exponent. So in this case, you might actually want to try to do some kind of reinterpreting cast on some of the bits in A. And this gets kind of advanced and not really going to cover it any further in this class. Just want you to know about it. It's also dangerous because it often depends on knowing the underlying machine architecture, so it's often a non-portable operation, but it does allow you to get additional speed, and system programmers will often use it when they implement kernels. So just to wrap up, you need to, with their type checking, make sure that you understand the difference between type conversions, which are explicit conversions by the programmer, what we often call casts, type coercions, which are implicitly done by the compiler, and it does them when the types are compatible.